In this non-uniform circular motion, the object may be revolving in a circle or is moving in any curved path, not necessarily a circle. And as we know, any segment of the path, the curved path, may be considered approximately as a circle. In this scenario, we have always the radial acceleration, or the centripetal acceleration called as well, is perpendicular to the velocity and also perpendicular to the tangent acceleration. So the resultant acceleration of the object in this non-uniform motion, which has two components, one along the radius inward and one tangent to the curved path or the circle, called AT, and they are both perpendicular to each other, and AT is defined as the derivative of the magnitude of the velocity with respect to time. Also, it could be positive or negative, it depends if it revolves counterclockwise or clockwise, while the centripetal acceleration, or sometimes called radial acceleration, is always towards the center and has a minus sign. These two components can be used to get the magnitude of the resultant acceleration by using the Pythagorean theorem, and also the angle between the total acceleration and the radius is taken usually this angle with respect to the radius. It's nothing more than tan inverse of the tangential component divided by the radial component. So in this case, we managed to have the magnitude and direction of the resultant acceleration in this type of motion. As an application to the non-uniform motion, let's take this example for a particle moving in a clockwise direction in a circle of radius 2.5 meters, and at a certain instant of time it has an acceleration of 15 meters per second when it was 30 degrees with respect to the radius. Now you need to find radial acceleration of the particle and the speed of the particle in addition to the tangential acceleration. To solve part A of problem, that is finding the radial acceleration of the particle, this is just straightforward. You have to look at this triangle where you have an angle of 30 degrees, and the side of the triangle, the blue one, is AR, and AR is equal to A cosine theta by plugging in all the values of the angle 30 degrees and that of the magnitude of the acceleration. You get an answer of 13 meters per second square. To find the speed of the particle, simply applying the relation for the centripetal acceleration, that is v square or r, just the magnitude, and we got 13 meters per second for the acceleration and 2.5 for the radius. Put that in and you get the velocity or the speed equals 5.7 meters per second. To find the tangential acceleration, also again, the tangential acceleration is the opposite side of the triangle to the angle 30 degrees. So A sub t, tangential acceleration, is equal to, in this case, A sine 30, and then you put 15 meters per second for the acceleration and you get an answer for tangential acceleration of 7.5 meter per second square. Obviously, there is another way of getting the tangential acceleration. You can get it from Pythagorean theorem, as long as you have 15 meter per second for the resultant, and one of the component AR is you have it as 13 meter per second, then you can get it from the Pythagorean theorem as well. In this exercise, a train slows down as it goes around a horizontal sharp turn by going from a speed of 90 kilometers per hour to that of 50 kilometers per hour in 15 seconds time. The radius of the curve is 150 meters. Determine the acceleration at the moment that the train reaches the speed of 50 kilometers per hour. And you are given here an assumption that the train slows down at this moment at the same rate. And an answer is given for the acceleration of 1.48 meter per second square. That is with an angle of 29.9 degrees backwards. Here is the train as shown at the bend curve at point A with a velocity of 90 kilometers per hour, and also the figure or the picture shows the radius of the curvature. This picture shows that the train overcome the turn to point B, where its velocity becomes 50 kilometers per hour, and also shows the time as the train goes from A to B. The elapsed time is 15 seconds. Here the picture again shows the initial position of the train A with its initial speed of 90 kilometers per hour, and the final position where at B, where its speed becomes 50 kilometers per hour, and also given the time it takes the train to go from A to B, and also the radius of the curvature. To solve this problem, it will be better to convert the dimensions or the units from kilometer per hour for the speed to meters per second. Then this is the first step. By doing that, we get v sub a, the speed at point A, as 25 meters per second, and that for B, speed at B, as 13.9 meters per second. Then the next step is just to apply the formula for the radial acceleration or centripetal acceleration as v square over r, inserting these numbers, the number obtained for at this moment for the speed at the moment of 15 seconds, that is at point B, insert the number of 13.9 meters per second as requested in the problem, and that is divided by the radius of the curvature. You will get an answer of 1.29 meters per second square. For the tangential acceleration, we have to use the approximation given in the problem by assuming that the time interval takes the train to go from A to B very small. This will allow us to consider that the tangential acceleration at this moment is equal to the average acceleration, and the average acceleration is equal to delta v over delta t, and delta v is, as we know, is the final speed minus the initial speed divided then by the time interval of 15 seconds. You will get an answer of 0.74 meters per second square. The minus sign is an indication that there is a deceleration in this in this motion, in this tangential motion. As long as you have two components, one along the tangent and one along the radius, we can get the resultant of this acceleration by using Pythagorean theorem. And by inserting the obtained values, we're going to get an answer of 1.48 meter per second square. The angle is going to be taken with respect to the radius, as we said before. The angle of the acceleration is tan inverse the tangential component divided by the radial component. And by plugging in the values by including the sign as well, we'll get an answer of minus 29.9 degrees. The minus sign is an indication that the motion of the train is the acceleration of the train is opposite to the direction of motion of the train.